Students, today's topic of my lecture: electric flux, Gauss's theorem and its applications. So before starting electric flux, you must understand area vector, because in some applications we have to take area as a vector. Generally what we say, area is a scalar quantity, but in many problems area is to be taken as area vector. So what actually its meaning? Its meaning is that you have to take a surface, and on that surface you draw a normal in outward direction. Always you remember it. The normal which is drawn on the surface is in outward direction. Then the length of the arrow that represents the magnitude of the area, and the normal drawn outward on that surface gives the direction of area vector. So here we take a small area element delta S over to a surface of area S. Then we draw a normal in outward direction over to this area element delta S. Then that can be represented by delta S vector equal to delta S n cap, where this delta S is the magnitude of the area element and n cap is the unit vector which gives the direction of outward normal at that point. Then this is the representation of the area vector. Now come to the electric flux. So first you understand the meaning of the flux. Flux means flow. So I just remind your memory that you have studied in class 11 while you are driving a equation of continuity. At that time you have studied the volume flux, that is the number of streamlines of the liquid passes through an area of a tube per unit time normally and comes out streamlines through the other end of the tube normally, then that is called volume flux. Similarly, we can define electric flux to a surface placed in an electric field, that is the total number of electric field lines passes to the surface normally. This normally word is very important, so you just remember it while you are defining the definition of electric flux. Now here you see that there are three diagrams I have taken. In the one diagram, the surface which I have taken of the surface area S, and which is placed in such a way that the number of electric field lines that passes through that surface area S. In that condition, if we take a small area element over to this surface, say delta S, then we draw a normal outward. Then the direction of the area vector and the electric field both becomes in the same direction. That is, angle between them is 0. But in the second case, if we take area and we tilt it, that is, area vector makes some angle with the direction of electric field. Say here it is theta. So in that condition, when you resolve this area vector, then its component delta S cos theta that comes in the direction of electric field, or you resolve electric field component along the direction of area vector, that is E cos theta. Now in the third condition, field lines, they are touching the surface S tangentially, means they are not passing through the surface. In that condition, the angle between area vector and the E vector is 90 degrees. So electric flux delta phi through an area element delta S can also be defined as the product of magnitude of electric field and the component of area vector, or you can also define as the product of magnitude of area vector and the component of electric field along the direction of area vector. Then this E delta S cos theta can be written as the dot product of electric field and area vector, that you have already studied in class 11. Dot product of two vectors A dot B equal to AB cos theta. Now you see that here we have taken a surface of area S. Then this surface S having the large number of the small area elements. Then the total electric flux over to entire surface can be defined as phi approximately equal to sigma, that is the summation of electric flux over to the small area element. So phi approximately equal to sigma E vector dot delta S vector. So there is a specific purpose for taking this approximate sign. Before explaining that, you must understand that when you are saying that delta phi equal to E delta S cos theta. So in first case, what happens when theta equal to 0, then what you are getting? The electric flux. Delta phi equal to EA or E delta S cos 0. Cos 0 is 1. So delta phi equal to E delta S. That is the maximum electric flux. So that's why we say that the surface normally. But in case of the second case, theta angle, and the angle theta can be any value. Say here we are taking the third case when the theta is 90 degree. In that case, delta phi equal to E delta S cos 90 degree, and cos 90 is 0. So delta phi equal to 0. Obviously, because the number of field lines, they are touching the surface tangentially, they are not passing through it. So that is called electric flux. Now, why we are taking this approximately sign? So you understand this one like that. Now here we are taking approximation sign in equation 1 because the electric field here we have taken a constant over to a small area element. That's why mathematically, exactly if you want to write, then we say that we can put a limit delta S tends to 0. Then the summation in equation 1 can be written as phi equal to surface integral E dot ds equal to Es cos theta, or dot product of E vector and S vector. Now here you understand again. Here we have taken one closed surface. So here you can see that all cases, and this closed surface is placed in an uniform electric field. So when we placed in uniform electric field, then you see here direction of the electric field, and we take a small area element ds vector drawn in normal outward, then both are having the direction same. So angle between them is 0. Whereas if we take here the area element, then this area element makes an angle theta with the direction of electric field. Similarly, if we take area element here, then it makes an angle 90 degree with the direction of electric field. Same way here and here. So if we want to calculate total electric flux over to this surface, then what we have to do? We have to integrate over to whole surface E vector dot ds vector equal to es cos theta, which is equal to E vector dot S vector. So it means we have to calculate the electric flux over to a small area element, and after that we integrate it. Then we get total electric flux over to the entire surface. Electric flux is a scalar quantity and its SI unit is Newton meter square per coulomb. How this unit comes? See here, electric field is represented in Newton per coulomb. That is, SI unit of electric field is Newton per coulomb, and the SI unit of area is meter square. So it becomes Newton meter square per coulomb. Another unit of electric flux is also, that is volt meter, and that you understand when you find a relation between electric field intensity and electric potential. From there you get a relation between electric field intensity and electric potential. So from there we calculate this unit of electric flux. So when you calculate the relation, at that time you understand this unit. Here you just remember it, because in CBSE examination so many times question comes on the basis of units. They write the units and ask name of physical quantity which has this unit. So you must remember it. Now we take one example, as we are saying that if we are tilted the area which makes some angle with the direction of the electric field, then how much electric flux through the surface. So you understand this by taking the two examples here. The first question is, an electric field of 200 Newton per coulomb makes an angle 60 degree with the surface vector. Then it has the magnitude of 0.500 meter square. Then find the electric flux that passes through the surface. So here you see that what is given to you. Electric field is given to you, angle is given to you, and area is given to you. And then you apply the formula which you have studied. Phi E equal to E vector dot S vector equal to ES cos theta. So E is given 200 Newton per coulomb. Area is given 0.500 meter square. Angle theta is 60 degree. So cos 60 degree. So when you calculate it, then you will get phi E equal to 50 Newton meter square per coulomb, or 50 volt meter. Another question we take, a uniform electric field E equal to 3 into 10 to the power 3 I cap Newton per coulomb. It means the electric field is acting along the positive x direction. What is the flux through this field through a square of 10 centimeter on a side? Means you have to calculate the electric flux through a square of side 10 centimeter whose plane is parallel to the YZ plane. Whose plane is parallel to YZ plane. So you remember it, just you make the diagram in your mind. Then what you will get, plane of the square which is parallel to the YZ plane, it means it is along to the positive x direction. So the angle between electric field and the area vector of square is 0. So you apply the formula phi E equal to E vector dot S vector, which is ES cos theta. E is given to you 3 into 10 to the power 3 Newton per coulomb, and area is given 0.1 meter into 0.1 meter. Since the side of the square is given 10 centimeter, so convert it into SI unit, that is 0.1 meter, and the area is 0.1 meter multiplied by 0.1 meter, and cos 0. Cos 0 is 1. So after calculating, what you will get? Phi equal to 30 Newton meter square per coulomb. So these are the two examples that we have taken so that you can understand how the flux gets changed with the direction of normal vector with electric field, or when you are changing the position of area of the surface with the direction of electric field. Now, very important topic, Gauss's theorem or Gauss's law. So you understand this theorem or this law carefully, because every year in your CBSE board examination, one question you will get from the Gauss's theorem or the Gauss's law and its applications. So according to this law, the total electric flux through any closed surface in vacuum is 1 upon epsilon naught times the total charge enclosed by the closed surface. Earlier what we have taken? We have taken a surface, whether it is an open or it is a closed. But here it is specifically we are writing that the total charge enclosed by closed surface. Right? So you remember it. So further you understand, according to this theorem, the total electric flux through any closed surface in vacuum is 1 upon epsilon naught times the total charge enclosed by the closed surface. So in that condition, according to the definition of the electric flux, phi E equal to, here the closed surface is there, so we have to use a closed integral, means integration sign, and in this integration sign our open circle you place, then its meaning is that closed integral over to the surface S, E dot ds. So this becomes total electric flux through a closed surface. As per Gauss's law, that must be equal to 1 upon epsilon naught the total charge enclosed in the closed surface, that is sigma I equal to 1, I equal to n qi, or you can say that capital Q upon epsilon naught. So here the capital Q is the total charge enclosed by the closed surface. Now we have to derive whether this statement is correct or not. So for that purpose, you must first understand the Gaussian surface, because while you are driving Gauss's law or the Gauss's theorem, you must know the Gaussian surface, because we have to choose a Gaussian surface for driving the Gauss's law. Gaussian surface around a charge distribution, whether it is a single charge or large number of charges, is a closed surface such that electric field intensity at all points on the surface is the same, and electric flux through the surface is along the normal to the surface at every point on the surface. So you understand, Gaussian surface always encloses the charge, and electric field intensity at every point on its surface must be the same, and electric flux through the surface is along to the normal to the surface at every point. You remember it. I just give one example so that you can understand in much better way. we take a spherical surface and placed a charge at its center. So when you place the charge at its center, then this charge distance from surface or at every point of the surface of this spherical surface is the same, that is equal to the radius, and electric field intensity that depend on to the distance. So here in this case of spherical surface and the charge is placed at its center, the distance becomes same for every point on its surface. Then electric field intensity at every point on the surface of this spherical surface becomes equal, and electric field flux is also normal at every point. Then we say that that surface is Gaussian surface. So for driving Gauss's theorem, we have to first consider a Gaussian surface and place the charge at its center. You see here, consider a single point charge plus q placed at the center. As you see in the diagram, here we take a spherical surface that we are saying that it is a Gaussian surface. From the definition, you also understand that if we place a charge at its center, then the distance of every point on the surface of this sphere is the same. So that's why the electric field intensity at every point on its surface is the same, and the flux is also normal at every point, right? So for defining the Gauss's law or driving the Gauss's law, first we have to choose a Gaussian surface. Then you see here, on the surface of this Gaussian surface, we take a point P. So at this point P, you concentrate that this plus q charge placed at the center. Then due to this plus q charge, direction of the electric field is radially outward. Then we take a small area element, that is delta S or ds vector, and direction of this ds vector is outward. So angle between E vector and ds vector is 0. You can see here. Now, in the definition of the Gauss's law, what we are saying that total electric flux over to a closed surface is equal to 1 upon epsilon naught times the total charge contained by the closed surface. So what we have to do for driving this Gauss's law? We have to find out total electric flux through this Gaussian surface. So you see here, total electric flux passes through this closed surface. By the definition of the electric flux, phi E is equal to closed integral E vector dot ds vector. Since angle between E vector and ds vector is 0, so therefore closed integral E ds cos 0. Since cos 0 is 1, so that's why, which is equal to closed integral E ds, or we can say that phi E equal to, you take E outside, since E is constant, that is, it is at every point onto the Gaussian surface, it is same. Then E you take outside the closed integral, then inside is ds. Then electric field intensity at every point onto the Gaussian surface, as you already know that the electric field intensity at a point due to the point charge plus q is E equal to 1 upon 4 pi epsilon naught q upon r square. So same that you have to write here, q upon 4 pi epsilon naught r square, and the area, that is the area of the spherical surface, 4 pi r square. Then here you see that 4 pi get cancelled, r square get cancelled. What you will get? You will get only phi E is equal to q upon epsilon naught. So what you have said in the definition of the Gauss's law, total electric flux through the closed surface is equal to 1 upon epsilon naught times the total charge contained by the closed surface. So that is proved. Now if we say that there are n point charges, say q1, q2, q3 and so on, qn, lying inside the surface. Since flux is a scalar quantity, therefore according to the superposition principle, total electric flux is the algebraic sum of electric flux contributed by each charge and which are independent of others. That is, phi E is equal to phi 1 plus phi 2 plus phi 3 plus phi 4 and so on plus phi n. Now you calculate the electric flux due to individual charges. Say due to q1 is q1 upon epsilon naught, now q2 upon epsilon naught and so on. Take the algebraic sum, that is phi is equal to q1 upon epsilon naught plus q2 upon epsilon naught plus q3 upon epsilon naught plus and so on qn upon epsilon naught. You see here 1 upon epsilon naught is common. So phi E is equal to 1 upon epsilon naught, within bracket is q1 plus q2 plus q3 plus so on qn. Then you can rewrite it, phi E is equal to 1 upon epsilon naught sigma I equal to 1, I equal to n, qi, which is total charge. So in place of sigma I equal to 1, I equal to n, qi, we can write capital Q. Then phi E is equal to q upon epsilon naught. So this is Gauss's law or Gauss's theorem. So I hope you understand it. Now we take another concept, as what we are saying, charge enclosed by the surface. If no charge is enclosed by the surface, then what happens? Obviously, if charge is not enclosed by the surface, then the field lines, they will not pass through the closed surface. So in that condition, the total electric flux through a closed surface is 0. So this statement we have to prove, that the total electric flux through a closed surface is 0 if no charge is enclosed by the surface. So for that purpose, we consider a closed cylindrical surface with its axis parallel to the uniform electric field E. This is the axis of the cylindrical surface and this is electric field. So both are parallel. Now total electric flux through the surface is due to the contribution of the electric flux by these two flat surfaces of the cylindrical surface and this curved surface. So what we say that while we are calculating the electric flux, since it is the product of magnitude of electric field and component of area vector, or magnitude of area vector and component of electric field. So for that purpose we apply the formula phi is equal to E delta S cos theta or E S cos theta. See here in the two flat surfaces, already explained, when we draw a normal onto the area and that normal must be radially outward. So on flat surface 1, direction of area vector is opposite to the direction of electric field. On to the flat surface 2, direction of area vector is in the direction of electric field, and on to the curved surface it is perpendicular to the direction of electric field. So for the flat surface 1, angle between electric field and area vector is 180 degree, and for flat surface 2, area between area vector and electric field is 0. In case of curved surface, angle between electric field and area vector is 90 degree. So total electric flux through cylindrical surface, that becomes phi is equal to phi 1 plus phi 2 plus phi 3, that is algebraic sum of electric flux. Then phi is equal to Es1 cos 180 degree plus Es2 cos 0 degree plus Es3 cos 90 degree. Cos 180 is minus 1, cos 0 is 1, cos 90 is 0. So equation becomes phi is equal to minus Es1 plus Es2 plus 0. Now the flat surfaces of cylindrical surface having the same area, S1 equal to S2 equal to S. Then finally the equation is phi is equal to minus Es plus 0. Then it becomes 0. So what we say that if no charge is enclosed by the surface, then the total electric flux through the closed surface is 0. So that's why you remember it. The charge must be enclosed by the surface, then only you will get the total electric flux through the closed surface. Now we take one question so that you can understand in much better way. The question is that electric field in the given figure is directed along plus x direction and is given by Ex equal to 5ax plus 2b, where E is in Newton per Coulomb and x is in meter. So from here you just emphasize onto the language of the question. Electric field is directed along x direction. If it is acted along x direction, it means no electric field along the y direction and z direction. So there is no electric flux along y and z direction. So we have to concentrate only onto the positive x direction. Now A and B are constant with dimensions taking capital A equal to 10 Newton per Coulomb meter inverse and B equal to 5 Newton per coulomb. Then calculate electric flux through the Q and net charge enclosed within the Q. Very important question. This question is asked in your CBSE exam also. Now you understand the concept. In Y and Z direction, no electric field, so no electric flux. Now we have to concentrate along to the positive X direction, in which the electric field is applied. So you see here, along the positive X direction, there are two surfaces. One is represented by M, another one is by N. So first of all, what we have to do for calculating the electric flux? We draw normal on the surface which is acting outward. So on N surface, we have drawn a normal outward. Then the direction of this normal and electric field is the same. So angle between them is 0. But in case of surface M, the normal drawn outward, then the angle between area vector for the surface M and electric field is 180 degree. Whereas in case of N surface, the angle between area vector and electric field is 0 because both are in the same direction. Here they are in opposite direction. Then the total electric flux is the algebraic sum of flux due to the N surface and due to the M surface. So what we say that for the first part, phi is equal to phi M plus phi N. This is the algebraic sum of electric flux due to the M surface and N surface. Then you apply the formula phi is equal to Es cos theta. So here for M surface is Em Sm cos 180 degree plus for N surface En Sn cos 0 degree. Substitute the value of electric field which is given Ex equal to 5Ax plus 2B. Since cos 180 is minus 1, so that's why in next step is pi is equal to minus within bracket the value of electric field 5A and in place of x is 0 since M surface is at origin of the cube. So x is 0. So 5A into 0 plus 2B and then area of M surface Sm plus for N surface which is at 10 centimeter from the origin, that is 0.1 meter. So in place of x that we have to write 0.1 meter. So within bracket 5A into 0.1 plus 2B and then area of N surface. Now you substitute the values which is given in the question, that is A equal to 10 and B is equal to 5 and area that you have to take 0.1 into 0.1 for M surface and N surface. So equation becomes phi is equal to minus within bracket 5 into 10 into 0 plus 2 into 5, that is the value of B, into the value of area into 0.1 into 0.1 plus 5 into 10 the value of A into 0.1 value of x plus 2 into value of B 5, then multiplied by the area of N surface 0.1 into 0.1. Then you calculate it and then you solve. Then what you will get? You will get phi is equal to 0.05 Newton meter square per coulomb. So this is the total electric flux through the cube. Now in the second part, it is asked that what is the net charge enclosed with cube. So here you apply the Gauss's law. From the Gauss's law, you know that the phi is equal to q upon epsilon naught. So phi you have already calculated. Then q is equal to phi epsilon naught. Substitute the value. Phi is 0.05 and epsilon naught you know 8.85 into 10 is power minus 12. So when you solve it, you will get q is equal to 0.4425 into 10 is power minus 12 coulomb. So this much of the net charge enclosed within that cube. So this type of the questions you have to solve from your book. In NCERT, two questions are also given. One is of cube, another one is of cylindrical surface. So on the basis of this problem, you have to solve them, and two more questions, the same type, two more questions are also asked in the CBSE examinations, and that I will give you an assignment and then you solve it. Now applications of the Gauss's theorem. Very important. Every year one question you will get from the application of Gauss's theorem in your CBSE board examination. So first application is electric field intensity at a point due to an infinitely long uniformly charged straight wire. For understanding these applications, you must remember, first of all, you have to choose a Gaussian surface, and after that you calculate electric flux through the Gaussian surface. Then find out the charge enclosed by the Gaussian surface. After that you apply the Gauss's theorem. So these steps if you remember, then you will never forget the derivation of applications of the Gauss's theorem. So first application we are starting, electric field intensity at a point due to an infinitely long uniformly charged straight wire. So for that purpose we consider an infinitely long uniformly charged straight wire having the linear charge density lambda. If you remember, the linear charge density means the charge is uniformly distributed over to a line. So here this orange line that is representing an infinitely long uniformly charged straight wire having the linear charge density lambda. Now we choose a appropriate Gaussian surface. Here a cylindrical Gaussian surface that we have taken, and see here the radius of this cylindrical surface from the curved surface is at equal distance. If we take any point onto the curved surface, then which is at equal distance from the axis of cylindrical surface. Now we have the three surfaces here. One is flat surface A and B, another one is curved surface C. Then due to this uniformly charged straight wire, the direction of the electric field is radially outward. Here it is represented. If we take a curved surface, then we take a small area element on the curved surface at point C, that is ds vector. draw a normal outward, then angle between E vector and ds vector is same, that is 0. But when we take flat surface, say A, and area element we take ds vector, normal drawn outward, and the direction of the electric field, then the angle between area vector and the electric field is 90 degree. Similarly, when we take another flat surface B, normal drawn outward, and the angle between electric field and area vector is 90 degree. And the length of this Gaussian surface, cylindrical Gaussian surface, we are taking L. So what I told you that first we have to choose a Gaussian surface. Next step is find the electric flux through the Gaussian surface. So here you see that electric flux through the Gaussian surface, that is the closed integral equal to, that is the closed integral E dot ds equal to integral for flat surface A E dot ds plus integral for flat surface B E dot ds plus integral for curved surface C E dot ds. Means we are taking the algebraic sum of electric flux contributed by flat surface A, B and C. So as I already told you that in case of flat surface A, angle between E vector and ds vector is 90 degree. So electric flux contribution by the flat surface A becomes 0, or mathematically you can write closed integral E dot ds equal to integral for flat surface A E ds cos 90. Similarly, the angle between ds vector and E vector for flat surface B is 90 degree. So plus integral B E ds cos 90 degree. Now for flat surface B also the angle is 90 degree. So contribution of the electric flux is 0. Now for the curved surface C, the angle between E vector and ds vector is 0. So plus integral C E ds cos 0. So in case of flat surface A and B, contribution of electric flux is 0. So that's why electric flux you will get due to the curved surface. So E integral for curved surface C ds equal to, E is constant because at every point onto the curved surface from the axis of Gaussian surface is the same. Now the area of the Gaussian surface is 2 pi r L. So you are getting electric flux through the Gaussian surface equal to E into 2 pi r L. The next step I told you that find out the charge enclosed by the Gaussian surface. So you know that lambda is the linear charge density. So therefore charge enclosed by the Gaussian surface Q is equal to lambda L, where lambda is the linear charge density. When you calculated charge enclosed by the Gaussian surface, after that the next step that you have to apply Gauss's theorem. Then according to the Gauss's theorem, phi E equal to closed integral E dot ds equal to Q upon epsilon naught. Now flux you have already calculated, that is E into 2 pi RL equal to Q upon epsilon naught. But Q is equal to lambda L. So substitute the value here, then equation becomes E into 2 pi RL equal to lambda L upon epsilon naught. L get cancelled, then you will get E equal to 1 upon 2 pi epsilon naught lambda upon R. It means E is inversely proportional to R. Lambda is constant, 1 is constant, 2 pi epsilon naught is constant. So E is inversely proportional to R. In vector form, if you want to write, then E vector within bracket you take position vector equal to 1 upon 2 pi epsilon naught lambda upon R and R cap. R cap is the unit vector which gives the direction of electric field intensity. Now here on to the uniformly straight line, we have taken a positive charge. So that's why the direction of the electric field intensity is radially outward. But if we take the negative charge, that in that condition, the direction of the electric field intensity is radially inward. So you remember it. If we say that lambda is greater than 0, then the electric field intensity is outward. If lambda is less than 0, then electric field intensity is inward. Now we plot the graph between the electric field intensity and the distance. Then you will get the graph like that. Means if we increase the distance R, then electric field intensity decreases. Obviously, from this equation, it is very clear that E is inversely proportional to R. As R increases, then electric field intensity decreases. Now we take second application, which is also very important. That is electric field intensity due to uniformly charged thin spherical shell at first outside the point, second inside the point. You understand that we are taking spherical shell. Spherical shell means it is hollow from inside. So the charge which is given is distributed uniformly over to its surface. And then for finding the electric field intensity at a point outside, so as I told you that for any application of the Gauss's theorem, what you have to do? First, you have to choose an appropriate Gaussian surface, and after that you calculate electric flux through the Gaussian surface. Then in next step, find out the charge enclosed by the Gaussian surface. Then you apply the Gauss's theorem or the Gauss's law. Then you will calculate the electric field intensity. So here we take first part, that is at a point P outside the spherical shell. So here a plus Q charge is uniformly distributed over to the surface of spherical shell of radius capital R. Then we take a point P outside. Then for enclosing this charge, we take a Gaussian surface, that is a spherical Gaussian surface whose radius is small r, which is represented by green dotted lines. Then at point P, you focus direction of the electric field intensity due to the plus q charge is radially outward. We are taking here a small area element, and when we draw a normal on this area element outward, then the direction of the area vector and the electric field is in the same direction. So angle between them is 0. Now we find electric flux through the Gaussian surface, that is phi equal to close integral E dot ds. Since E vector and ds vector both are in the same direction, so angle between them is 0. So that is phi is equal to close integral E ds cos 0. Then phi is equal to, you take E outside, close integral ds equal to E. Since E is constant, so area of spherical Gaussian surface 4 pi r square. Now we say that let sigma be the surface density of charge. Then sigma equal to charge per unit area. Now you remember it. Here, area that you have to take, area of spherical shell, because the charge is distributed over to the surface of the spherical shell. So that's why charge enclosed by the Gaussian surface is Q equal to sigma A, and A is the area of the spherical shell, that is 4 pi r square. Then charge enclosed becomes Q equal to sigma 4 pi capital R square. Now you apply the Gauss's theorem. Then phi is equal to close integral E dot ds equal to Q upon epsilon naught. And this you have already calculated, and that is phi E equal to E 4 pi small r square equal to Q upon epsilon naught. Now from here, E equal to Q upon 4 pi epsilon naught r square. So you remember here, E is inversely proportional to the square of distance. Now since the charge enclosed by the Gaussian surface is Q is equal to sigma into 4 pi capital R square. So you substitute this value in place of Q, then you will get E equal to sigma capital R square upon epsilon naught R square after calculation. Here, one more important thing. The electric field which you are taking due to the uniform distribution of charge over to the surface of spherical shell, that is basically equal to the electric field intensity due to the plus q charge is supposed to be placed at the center of spherical cell. Since spherical cell is hollow, that's why the charge is distributed over to the surface. And because of this charge distribution, the electric field is equal to the electric field due to if charge is placed at the center of spherical shell. Then this derivation is valid. Now at a point on the surface of the spherical cell. On the surface of the spherical cell, it means small r is equal to the capital R. So from equation 1 we know that E equal to sigma r square upon epsilon naught small r square, and at surface small r is equal to capital R. Substitute this value in above equation, then it becomes E equal to sigma r square upon epsilon naught capital R square. Capital R square get cancelled, then E equal to sigma upon epsilon naught. This is the maximum electric field intensity at the surface of the spherical shell. So electric field intensity due to uniformly charged thin spherical shell at a point on the surface of the shell is maximum. Now we calculate electric field intensity at a point inside the spherical shell. So inside the spherical shell, we say that a point B, then we take a closed surface represented by these dotted lines. As you already studied that electric flux that we calculated and electric field due to the plus q charge distributed over to the surface of the spherical shell is supposed to be equal to the electric field placed at the center of the spherical shell. So that's why electric flux through this Gaussian surface is also equal to E multiplied by area of this Gaussian surface, which must be equal to 1 upon epsilon naught times the total charge contained by the Gaussian surface. So in the similar fashion, you have to find out electric flux through the Gaussian surface, that is phi is equal to close integral E vector dot ds vector. Since E vector and ds vector both are in the same direction, so angle between them is 0. Therefore phi is equal to close integral as E ds cos 0, that is E ds, equal to q upon epsilon naught. Then phi is equal to E, you take outside the close integral, inside is ds equal to q upon epsilon naught according to the Gauss's theorem. So area of Gaussian surface 4 pi r dash square. So flux is E into 4 pi r dash square equal to q upon epsilon naught. But the charge enclosed by this Gaussian surface is 0. So that's why E equal to 0 upon 4 pi epsilon naught r dash square. So in that case, electric field E equal to 0 inside the spherical shell. So this gives a very important property that earlier also we say that when I explained the electric field lines, that they move from surface to surface, that is from the one surface body to another surface body, starting from positively charged body and end at the negatively charged body. They are not the closed curves as magnetic field lines. Magnetic field lines are the closed curves, but electric field lines always lies from one body surface to another body surface. It means inside the body there is no electric field, that is no electric charge, and that property we have to use in a phenomena that is called electrostatic shielding, that I will explain you later on. So you remember this property: if there is no charge enclosed by a surface, then electric flux through that surface is always zero. Already you have proof when you are taking a cylindrical surface. Although these surfaces are placed in an electric field, even then the total electric flux through the surface is zero. That is the case of cylindrical body which you have taken. But here, inside the spherical shell, there is no charge. That's why electric field inside is zero. So you remember it. Don't get confused. In the previous cases that we have taken a cylindrical surface placed in uniform electric field but no charge inside it, so no electric flux through the surface. But here charge is distributed over to the spherical shell, and electric field intensity at a point due to this charge distribution is also equal to the electric field intensity if placed at the center of plus q charge. So you will get electric flux here, but electric field intensity is zero inside the charged spherical shell. Now we plot a graph. As we say that at the surface electric field intensity is maximum. So here you see that from O to this point R, this is the radius of the spherical shell, and at the surface you are getting the maximum electric field intensity, so which is represented by E max. And here this is the graph, means as the distance increases then electric field intensity decreases. That is, E is inversely proportional to R square. So this is about spherical shell. Now the third application is electric field intensity at a point near uniformly charged infinite plane sheet. So this is your third application. So again the same procedure you have to follow. First you choose a Gaussian surface, find out the electric flux through the Gaussian surface, then find out the charge enclosed by the Gaussian surface. After that you apply Gauss's law. So here we consider a uniformly charged plane sheet having the surface charge density sigma. This plane charged sheet is like that. So here charge is distributed and here the charge is also distributed. So the direction of the electric field intensity, since it is distributed by positive charge on both the side, so the direction is radially away. Same way on other side, like that. So we have to choose a Gaussian surface in the form of the cylindrical that passes through this uniformly charged infinite plane sheet, as you can see in the diagram. Then again we have to take the two flat surfaces of this Gaussian surface, that is A and B, and the curved surface we take C. So at flat surface A and B, direction of electric field is radially away. Drop the normals outward, then the direction of electric field intensity and the area vector is in the same direction. So angle between them is 0. Similarly, at flat surface B, the direction of electric field intensity and the area vector is the same. So angle between them is 0. Whereas in case of curved surface, angle between area vector and electric field is 90 degree. So first you calculate electric flux through the Gaussian surface, that is close integral as E vector dot ds vector equal to algebraic sum of contribution of electric flux due to the flat surfaces and curved surface. So that is integral A E dot ds plus integral B E dot ds plus integral C E dot ds. So angle for curved surface C is 90 degree. For the flat surfaces it is 0 degree. So in the next step, close integral as E dot ds equal to close integral A E ds cos 0 plus integral B E ds cos 0 integral C E ds cos 90 degree. So cos 0 is 1, cos 90 is 0. So that's why you will get integral EDS plus integral EDS plus 0. So this becomes 2E integral ds. Now integral ds, we say that total area is S. So this becomes total electric flux to the Gaussian surface equal to 2E into S. So the next step we have to follow, since we are saying that surface charge density sigma, then the charge enclosed by the Gaussian surface is Q equal to sigma S, where sigma is the surface charge density. After that you have to apply Gauss's theorem, that is phi is equal to close integral E dot ds equal to Q upon epsilon naught. So the electric flux that you have calculated 2Es equal to Q upon epsilon naught, and the charge enclosed by the Gaussian surface is Q is equal to sigma S. Substitute this value here, then you will get 2Es equal to sigma S upon epsilon naught. S get cancelled, you will get E equal to sigma upon 2 epsilon naught. Now if you want to write in the form of the vector form, then E vector and this L vector is the position vector, that is the length of the Gaussian surface that we have taken from infinite charge plane sheet equal to sigma upon 2 epsilon naught I cap. I cap is the unit vector. Now again, if we say that positive charge distributed over to the plane sheet, then the direction of the electric field intensity is radially outward. Whereas if we take negatively charged plane sheet, then the direction of the electric field intensity towards or radially inward. In other words, we can say that if sigma is greater than 0, then electric field intensity is outward. If sigma is less than 0, then electric field intensity is inward. So this is about the third application. Now in the next chapter you have to understand the concept of the capacitance. For that purpose we have to take a special case in the form of fourth application. Here we have to take two infinitely long plane sheet of charge, and they are having their surface charge densities sigma 1 and sigma 2, and which is uniformly distributed such that sigma 1 is greater than sigma 2. So this condition we are taking for calculating the electric field in three regions. You see in the diagram, we are taking two infinitely long thin plane sheets of charges, say A and B, having the surface charge density sigma 1 and sigma 2. Here this sigma 1 is greater than sigma 2. Now we take the three regions, region 1, region 2 and region 3. Here we have to find out the total electric field intensity. That you have already calculated electric field intensity due to the single infinitely long thin plane sheet of charge, and that is E is equal to sigma upon 2 epsilon naught, right? So here what we have to do, so first we take the direction of electric field. Since A sheet is positively charged, so the direction of the electric field is radially outward, and which is represented by E1 vector. And on the in the second region, if we see that it is also radially outward, and in the third region you see that radially outward. Similarly, in case of the plane sheet B, electric field is represented by E2, that is also radially outward. But you see in the second region, the direction of the electric field intensity due to the plate A and plate B is in opposite direction, and here it is E2 is represented and radially outward. In the three regions you just see, in region 1 and region 3, E1 and E2, they are in same direction, but in region 2 they are in opposite direction. So we use a sign convention. If two vectors E1 vector and E2 vector is in the same direction, then we have to take their vector sum, and if they are in the opposite direction, then also we have to take the vector sum. But in magnitude form when we write, then you remember it conventionally, if E1 vector and E2 vector they are in the same direction, then in the magnitude form the total electric field intensity E is equal to E1 plus E2. So in the first region and the third region, the total electric field intensity is E1 plus E2. But in the second region, they are acting in opposite direction. And since sigma 1 is greater than sigma 2, therefore direction of the electric field intensity is along to the direction of E1 vector. In magnitude form, then it becomes E equal to E1 minus E2. Now you substitute the values of E1, E2. That is, E1 is already you have derived due to the single seat, sigma upon 2 epsilon naught, and E2 is sigma 2 upon epsilon naught. So when you substitute, 2 epsilon naught is common. So this becomes E equal to sigma 1 plus sigma 2 upon 2 epsilon naught. And in the second region, E equal to sigma 1 minus sigma 2 upon 2 epsilon naught. In the third region, E equal to sigma 1 plus sigma 2 upon 2 epsilon naught. So this is the case when you are taking two parallel infinitely long thin plane sheet of charges. So here we have taken the condition that sigma 1 greater than sigma 2. Now we take a special case. If sigma 1 equal to sigma and sigma 2 equal to minus sigma, that concept we have to use in next chapter, that is in capacitance. So that's why you must understand that concept here and apply that concept in capacitance. So the next special case is if sigma 1 equal to sigma and sigma 2 equal to minus sigma, then what you will get? Electric field in region 1, region 2 and region 3. So you see here, when we are taking plate A having the surface charge density sigma, that is positive charge distributed. When we take plate B, surface charge density minus sigma, then a negative charge is distributed. So in that condition, see the direction of the electric fields. Due to the plate A radially away, represented by E1, here also radially away, and here it is also radially away. But due to the negative charge, electric field radially inward, which is represented by E2. So you see, in region 1, E1 and E2, they are in opposite direction. In region 2, both are in the same direction. In region 3, they are in opposite direction. So in the magnitude form, when you write total electric field intensity in region 1, and that one is E equal to E1 minus E2. Whereas in case of region 2, both are in the same direction, therefore E equal to E1 plus E2. In third region, again they are in opposite direction, so E equal to E1 minus E2. Substitute the value of E1, E2, that is sigma 1 upon 2 epsilon naught minus sigma 2 upon 2 epsilon naught, as you have done in the previous case. So when you substitute in place of sigma 1, sigma, and here in place of sigma 2, sigma, because already minus sign is there, so that we are saying that the B plate is having a minus sigma surface charge density. So electric field is 0 in region 1. And when you substitute here, because we are taking a magnitude, so we are putting the value of charges also in the form of the magnitude. So here in place of E1, sigma 1 plus sigma 2 upon 2 epsilon naught. So when you substitute the condition, above condition, then in place of sigma 1 sigma, in place of sigma 2 sigma. Then it is becomes 2 sigma upon 2 epsilon naught. 2 get cancelled, only sigma upon epsilon naught. Similarly, in the third region, when you substitute the value, then again you will get a 0. That is sigma minus sigma upon 2 epsilon naught. Right? Now you remember it. Why we are substituting here in place of sigma also sigma and sigma 2 also sigma? You can say that you are saying that here sigma 1 equal to sigma and sigma 2 equal to minus sigma, but here you are not putting here in place of sigma 2 minus sigma. Why we are not putting this? Because we have already taken the direction of electric field intensity because of these plus sigma and minus sigma, because of the plus q charge and minus q charge. That's why the direction of the electric field intensity in the second region is in the same direction for both the plates. And in case of region 1, they are in opposite direction. In case of the region 3rd, they are in opposite direction. So that's why here we have to take only in place of sigma to sigma in all three cases. That's why you are getting here 0, and here you are getting sigma upon epsilon naught, and here you are getting 0. So from here you will get a concept that if both the plates are having equal and opposite surface charge density, then only the electric field will lie in the second region, that is between the plates, and on the either side of two plates the electric field is 0. So you remember this concept. That concept we have to apply in the chapter of capacitance. So if you like my video, then like it, subscribe and press the bell icon. Have a nice